Hello, everyone. I'm José Pereira, and on behalf of University of Coimbra team and State University of Coimbra team, I'm going to present this paper, which is called A Platform to Enable Self-Adaptive Cloud Applications Using Trustworthiness Properties, uh, which we are going to present what was developed for the Atmosphere project, which was a project that lasted from 2017 until 2019, and it was an European and a Brazilian project. Okay, I will start with the motivation, and then I will move to the contributions. I will talk a little bit about the background and related work. Then I will move to the trustworthiness framework that we proposed, as well as the TMA platform, which is also available online for you to check it. I will also show a usage scenario that we presented in the paper, and then I will conclude with future work. So the motivation for this work is that cloud applications need to be monitored in regards of trustworthiness, both in design time, so while the application is being developed, and also during runtime to avoid losses. Because in a cloud environment, we do know that if the application is not available, it's money that is being spent, because usually in a cloud application, you pay per use of the environment. Okay, but trustworthiness is not an easy property, because it's composed of many other properties such as reliability, availability, security, privacy, dependability, and others. Also, the current cloud providers allow adaptations based mainly on CPU usage and memory consumption. And our goal is to have a solution that allows adaptations based on other properties such as security, privacy, fairness, other properties that are related to trustworthiness, as well as the main property of trustworthiness. So the contributions of this work are an assessment and improvement of the trustworthiness of cloud applications. And we are also going to show a solution for cloud applications without needing to start developing a self-adaptive mechanism from scratch. So that's why we have the TMA platform, which is the Trustworthiness and Monitoring Assessment Framework platform. Some background and related work. So one of the main goals for our work is the MAPK, which was suggested by IBM years ago with probes and actuators. So inside this adaptation loop, we have a way to reason over the data and decide about the adaptations that are needed in a cloud application, and also some cloud autoscaling solutions such as Amazon Web Server autoscaling services, as well as Kubernetes horizontal pod autoscaler for Docker containers deployed in a Kubernetes cluster. Our framework is composed of several items, such as properties and metrics to characterize framework, a life cycle with two phases, which I'm going to show to you in our next slide, a monitoring platform that allows us collecting measurements and events from a cloud application, some measurement instruments to gather the information, also known as probes in our context, but in the literature, we're going to also see this called as sensors, quality models, which will allow us to aggregate the data and come up with a score for each one of the properties, and actuators that will allow us to adapt this cloud application through our framework. So our framework, our life cycle is composed of two main phases, one for design time and another one for runtime. The first one is for design time. So as soon as we build it and we measure the application, we are going to run trustworthiness tests. And if the trustworthiness is achieved, the goal, our goal, we are able to deploy the application. As soon as we deploy the application, we are going to go to runtime phase. And in this runtime phase, we are going to have a MapK cycle that we're going to monitor, analyze, plan, and execute our application. So we will be collecting data. We are going to reason over those data. We're going to plan some actions if adaptations are needed, and we are going to execute. We're going to invoke the actuators to perform the adaptations. Okay. So our framework, this is a quick architecture of our application. In the main blue box that we have here, we have our trustworthiness and monitor assessment platform, which we also call it as TMA. And the TMA has three main interfaces. The first one is the monitor interface, which will allow us not only the runtime probes to send data, but also during design time, they will send data through this REST interface that we have for the monitor. And we have several components here, all of the MapK components here. We also have the Actuator API interface, which we can also which will invoke actuators from the management system, which in our case is a cloud application, or this actuator can be invoked by the user. Okay. This architecture is also deployed in a Kubernetes cluster. So each one of the components is designed as a microservice. Each one is deployed in a pod from Kubernetes. And we also have a fault-tolerant queue that will allow us communicate with all of the components. Okay. And we also have a knowledge database. And this knowledge database has an API that will allow interacting with our system as well. I will detail about each one of the components right now. So the first one is the monitor component. Like I said, it has an interface to be invoked by the probes, and the communication is secure with SSL certificates. All of the items are sent to the monitor, which has a Flask microservice, and it will add the items to this topic from Kafka. And we also have a component from knowledge that will be checking that topic and will be inserting the data in the database. Okay. The analyze component is the second one. This component is responsible for checking the new data that is being inserted in the database. And as soon as we have new data, we are going to calculate the trustworthiness scores. The trustworthiness scores are calculated as an aggregation of each one of the properties of trustworthiness. Okay. We have an example here of how we're going to do that. And this is done through a quality model. And the quality model that we are showing to you here is a performance quality model. Okay. So in order to come up with the final score of trustworthiness, we needed to aggregate several quality models. For this particular case, we have a tree structure, and we have weights for each one of the nodes of this tree. For the leaves that we have in this tree, we have the data that are collected from the probes. Probably we need to aggregate this information somehow, maybe calculating the average of a period of time. And then we have some weights And we also have operators to aggregate each one of these items. So this is done until we come up with a final score, okay? So we have attributes, we have weights, we have operators, and we have this structure of a tree. Then we have two other components. We have a planning component and an execute component. The planning component will check each one of the scores that are being calculated by the analyze component, and we'll check if the score is achieving the threshold that was defined in advance. In case the scores are not according to the thresholds, we are going to create an adaptation plan. This is done in our case using a Drew's rule, which is what we have here in this slide. And this Drew rules checks it and creates this action. Drew's is a business management system, business rule management system that is more business oriented, and that's good from rules that is easier to read. Then, when we have new plans, someone needs to invoke the actuators to perform the needed adaptations. Executor is responsible for that. So, executor will check for new plans, and in case we have new plans, executor will invoke the corresponding actuator through the REST API interface that the actuators have. Okay. Finally, we have a last component, and this last component is the knowledge component. For the knowledge component, we have data models for each one of the areas that we need. We have a measurement and events data model, which we have represented here. We have a metrics and score data model, and we also have an adaptation data model. Like I said to you before, we also have a way to interact with the knowledge base, either through a REST API or through a graphical user interface, which we are showing to you in this picture. Okay. For this paper, for this demo, we created a usage scenario, which we created 4 different configurations. Okay, the first one is when we don't have any adaptation at all. Then we have one with Kubernetes HPA adaptation. Then we have 2 adaptations based on our quality models. One using the performance quality model, which was the one that I showed to you before, and another one using the resource consumption quality model. We are using this scenario in a cluster, in a Kubernetes cluster, which is composed of a master node, 2 working nodes, and a storage node, which we have set. The scenario that we are going to test is also our web application that we are going to increase the load of it, and we need to check how it will behave. Okay, this web application is also deployed in a Kubernetes cluster, and this web application allows us to scale up and scale down, so we can add more pods, add more containers in case we notice that some change is needed. Okay. The charts that I'm going to show to you right now are going to show both the performance score and the resource consumption score. And we want to check how it evolves, okay? Even if we are not adapting using those scores in all of the cases, of course, in cases C and D, we are going to use them to adapt. We want to check how the system behaves and how the score behaves throughout this scenario, okay? So the first one is without an adaptation. And it's important to mention to you that performance score is a cost score. In other words, this means that if we have the performance score is the resource consumption score is a cost score. So if we have high values of the score, this is bad. So for the resource consumption score, we want to spend less. And the performance score is not like that. It's a benefit score. So we want to use less of it. We want to use more of it. The more, the better. Okay. So as we can see here, we dropped it around second 111. We dropped the performance score and we increased the resource consumption score. And this is bad because we made no adaptations at all. Okay, but the scores changed accordingly. For the second case, we also have the same, but the performance score kept almost the time the same. And the resource consumption score, we had a few peaks in the middle of each, the resource consumption increased, and we have a plateau here. And after, by the end, we decreased this score as well. Okay, this is the adaptation performed by Kubernetes HPI. For these two other scenarios, we are adapting based on performance and on resource consumption. For this one, it's based on performance. So we can see that the performance increased here, and this is related due to the increase in the number of available pods. We also had an improvement in the performance. And we can also see that the resource consumption also increased because as we had more pods, we had more memory and CPU usage being used. Okay, and that's a side effect of it. And finally, for the resource consumption quality model, we noticed something pretty similar. The performance increased, the resource consumption also increased due to the addition of these items. But the system, the performance as a whole was better, okay? This is the same table that will summarize the results of each one of these charts that I have just shown to you. And we can see that some adaptations were made. So every time that we have a star in the cells, either a scale up or a scale down happened during this process. For the scenario B, we can notice that we were using HPA. We can notice that we have one scale up, and through all the time during this experiment, we didn't scale down, okay? Something different happened in the scenarios that we were using our system, our TMH to perform the adaptations. So we scale up, then we scale down, then we scale up again, then we scale down again, both using performance and resource consumption. So we didn't want to have idle components, okay? And that's the goal as well. For future work related to TMA, we want to add other trustworthiness quality models related to other properties as well. We already have some related to privacy, for instance. We also want to allow the user to create their own quality models. So we have a dashboard in our analyze component. We also want the user to create their own quality models. And we also want to use design time quality models to be integrated in continuous integration workflow. So in case some of the scores are not met, then we want to prevent the deployment of the application. So I hope to talk to you on the 30th of June, and then I can show to you a demo of our application as well. Thank you. Bye.